That's good. So thank you, David, for the introduction, and good afternoon, everyone, and welcome to our presentation today. So today we will be talking about the digital planning of the fourth treatment stage with powder activated carbon for the removal of micropollutants. So the work to be presented here was done within the framework of a joint research project funded by the Ministry of Environment, Baden-Württemberg, in coordination with partners from Karlsruhe Institute, the Institute of Wasser- und Gewässerentwicklung, die Kompetenzzentrum Spurenstoffe und Weber-Ingenieur. So I will start with some basics. What are micropollutants? The term micropollutant basically represents the residues of chemicals such as pharmaceuticals, cosmetic products, pesticides, and biocides. These are released into the hydrological cycle, mainly mainly through the pathways shown here, as you can see, from farms, towns, households, hospitals, and healthcare centers. When we take, for example, medicines like ibuprofen, diclofenac, they're exerted with urine and they reach to the sewer systems. They're also gets to exerted from industries, and these micropollutants or chemicals gets to the natural water bodies directly through runoff or from wastewater treatment plants effluents, and eventually they reach water treatment drinking plants. So micropollutants have been detected in wastewater treatment plants effluents and also in drinking water bodies. The issue of micropollutant removal has been a growing global concern due to their potential ecological risks. Although the long-term effect on humans is still not known, but they can harm several aquatic organisms, even at extremely low concentrations. Studies have shown that some of these micropollutants cause behavioral change in fish and results in the feminization of young male fish. And since conventional wastewater treatment plants are unable to eliminate these micropollutants, new methods and new approaches have to be developed and integrated into wastewater treatment plants. So the removal of micropollutants from wastewater can be achieved through three main mechanisms. We can remove them either through adsorption into a solid surface like activated carbon. We have powdered or granular activated carbon, or physically through nanofiltration and reverse osmosis, or we can remove these micropollutants can be oxidized with ozone or through advanced oxidation processes. And the most promising approaches are highlighted here in red. So here I have small diagrams for the promising or the most popular methods for micropollutant removal. In the first one, you can see here we have a granular activated carbon filter, which usually follows the biological treatment. And the second one, we have ozonation with ozone generator. And the third one here, we have all of them are within using the powder activated carbon, so adsorption into powder activated carbon. But what is different between these three processes is basically where the powder activated carbon is dosed. So we have three main approaches. Either we dose the powder activated carbon in the biological treatment, so in activated sludge tanks, or before a filter, or what is known as the Ulm-Verfahren, so Ulm method. It's basically we have a contact reactor where the powder activated carbon is dosed, and this contact reactor is followed by a sedimentation tank. And there will be internal recirculation of powder activated carbon. And this process is followed usually by a filter. So now let's dive a bit into chemistry. So I've been talking about adsorption. What is adsorption? So adsorption is basically a phenomenon that results in the adhesion of molecules. In our case here, it's adhesion of micropollutants into a solid surface, which is powder activated carbon. And the adsorption equilibrium of a single adsorbate, so if we have only one component in our water, the adsorption equilibrium will be a function of the equilibrium concentration of that adsorbate. So how much liquid phase concentration of that adsorbent is present. And usually it is described by what is called adsorption isotherms. So as you can see here in this equation, we have Q is the adsorption loading, which is basically the amount of micropollutant or whatever component I have in water divided by the mass of the adsorbent, which is a function of the equilibrium concentration in water at a constant temperature. What are adsorption isotherms? So basically, these isotherms demonstrate the amount of material that is being adsorbed per unit mass of adsorbent. So how much micropollutant will be removed or adsorbed, but per how much powder activated carbon I have. And this is described usually as a function of equilibrium concentration, as shown here. Several adsorption isotherms have been developed, but here I will discuss only, or I present only the most important two, which are the Langmuir and Freundlich isotherm. Both of them are two-parameter single solute isotherms, but however, the Langmuir isotherm is not very suitable to describe experimental isotherm data for aqueous solutions. The Freundlich isotherm, on the other hand, is widely used for describing the adsorption from aqueous solution, and in particular, powder-activated carbon. And that's because we have here the exponent, Freundlich exponent n, and which takes this adsorbent surface heterogeneity into account. That's why it's very suitable for adsorption for PAK. And previous studies have shown that the Freundlich isotherm meets better fitting results when it comes to powder-activated carbon adsorption. These two isotherms were for single solute, so if I have only one component in my water. But what if I have more than one adsorbable component? So what if I have in my water more than one micropollutant? I have diclofenac, ibuprofen, metoprolol, whatever. So the concentration, the equilibrium adsorption will not, of that component, will not depend only on the equilibrium concentration of that component, but adsorbates will compete on adsorption sites, on the adsorption site of the adsorbent surface, and the equilibrium loading of a certain component will not depend on its equilibrium concentration, but on the equilibrium concentration of all other components in the wastewater matrix. So for example, if I want to know the loading or the adsorption of metoprolol, I will have to know the adsorption of all other micropollutants in the wastewater system. And for that reason, the previously mentioned isotherms are not suitable by itself. So I have to, I need something more, a bit sophisticated for competitive adsorption. So I either use multi-solute adsorption isotherms, and I will not be discussing it here, but they're basically extension of Freundlich isotherm and other isotherms. And there is something called what is called the thermodynamic models. Under thermodynamic models, I have the ideal adsorbed solution theory, the vacancy solution theory, and the potential theory for multi-solute adsorption. So for the ideal adsorbed solution theory, it allows the prediction of multi-component adsorption. So when I have more than one component based on single solute isotherms. So from the data that can be acquired from the Freundlich, for example, or the Langmuir isotherms. And it is now considered the standard method for multi-solute adsorption. I also have the vacancy solution theory, which use 4-parameter single solute, not like Freundlich or Langmuir, which are 2 parameters. And the mathematical effort for applying VST is much higher than for applying the EST. We have also the potential theory for multi-solution adsorption, but this theory requires physical parameters such as solubilities and density, and they're afflicted with uncertainties. And it does not introduce significant advantage when compared to the EST, where when we're in the EST, these physical parameters are not needed. So in simpler words, EST is best. But so if we look at the how to solve these EST for given initial concentrations, because in batch adsorption system, usually initial concentrations are known. And the mathematical description for EST for known initial concentration based on Freundlich isotherm, as suggested by Wirsch, results in 2 main equations. These 2 equations basically are based on relating the initial and equilibrium concentrations by material balance equation and relating the partial loading to the total loading, QT. So solving these two equations with linear algebra solver gives the spreading pressure, phi, and also gives the total loading by keeping the smaller fraction, Z as a unity. However, we said EAST is best, but it's not perfect. So one prerequisite of EAST is that we must have a complete knowledge of solution composition. So I have to know exactly what is inside my wastewater, and by like quantitative and qualitative composition. So I have to know the isotherm parameters, and I have to also know the concentrations. And in water matrices, this is almost mission impossible, because I have what is called the background organic matter. And the background organic matter is a mixture of numerous compounds. Each has different quantitative and qualitative compositions. And in order to measure this organic matter, we usually use some parameters like SAC, SAK, or DOC. Also, the EAST fails to model the competitive adsorption between different micropollutants and background organic matter because it neglects the adsorption, the interaction between adsorbate and adsorbent. And also, it does not consider the different accessibilities of organic matter and organic micropollutant to adsorbed micropores. As you can see here, the micropollutants and organic matter, they compete on adsorption side through either direct competition on the external or internal surface, or through indirect competition, which is basically pore blockage, because usually the organic matter is larger than the micropollutants, and it hinders the transport of these micropollutants into the internal surface of the adsorbent. So in order to overcome the described problems associated with EAST, two modifications were developed. We have the equivalent background compound model, and we have the tracer model. The equivalent background compound model, it leaves all the organic micropollutant data unchanged, so it takes the isotherm parameters from single solute isotherm like Freundlich or Langmuir, and it does the correction needed for EAST by simplifying the description of organic matter. So for each micropollutant, it assumes that there is one equivalent background compound that is able to compete with this respective micropollutant. However, this method results in a complex factor because, for example, if I have 10 micropollutants or 20 micropollutants in my wastewater, then I will have 20 equivalent background compounds. On the other hand, the tracer model, it does the correction for EAST by modifying single solute organic micropollutant isotherm parameters, and the corrected parameters will usually are determined from experimental competitive adsorption. What does that mean? Basically, that when I want to calculate, or when I want to get the isotherm parameters, I do the experiments within the full wastewater matrix. So I will be testing the micropollutant adsorption with the presence of other micropollutants and organic matter as well. This will result in empirical multisolute isotherm parameters. And other thing for describing the organic matter, the TRM relies on the application of fictional components for OBC. For that reason, effective component approach was developed by Frick and further developed by others. So it basically this effective component approach is also called adsorption analysis, and the basic principle of this adsorption analysis consists in a transformation of the unknown multi-component system of organic matter into a defined mixture of limited number of effective components. So in simpler words, I say that, for example, my organic matter consists of 3 or 4 fractional components. Each one has different adsorption characteristics, and for that reason, each component will be characterized by different Freundlich parameters. For simplicity, we can assume that all of these fractions have the same N, have the same Freundlich exponent, but we changed the value of the Freundlich constant. For example, if I have non-adsorbable fraction of, and usually that's the case, of organic matter, then I will set the Freundlich constant to 0. Now, coming to the model, the model that was developed in the simulation tool Simba. This model is based on the tracer model as modification of EST and is combined with the Freundlich isotherm equation to calculate the single solid isotherm parameters. The ADSA concept, which is the adsorption analysis concept, was used for the fractionation of the organic matter. So looking at the different fractions considered in the model, so based on the ADSA concept, the adsorption analysis concept, the organic matter was divided into 4 different fractions, as you can see here: S0, S1, S2, and S3. So S1 is the non-adsorbable, S0 is non-adsorbable, S1 poorly adsorbable, and S2 moderately adsorbable, and S3 is good adsorbable organic matter. For each fraction, except for the S0, an X fraction, here as you can see X1, X2, and X3, represents the concentration in solid phase. So how much of this organic matter is getting adsorbed into powder activated carbon. And these matters have been assigned the same exponential Freundlich value, and was equalized for the 4, for the 3, and K value were set different for each of them. At the end here we have the we have only considered 1 micropollutant, and we have the last 4 fractions represent the PAK concentration and sludge fraction affecting the total sludge content and resulting total sludge production. So the model was developed and noted in a matrix format similar to the activated sludge model. And in the Peterson matrix shown here, we have, here are the different fractions that I presented. And we have 4 adsorption processes. So we have for each organic matter fraction, we have adsorption process, and we also have adsorption process for micropollutant. And we have also 4 desorption processes, as well as a process to present the biodegradation of micropollutants. So in order to calibrate the model calibration was done using experimental data from kinetic and isotherm studies obtained from Karlsruhe Institute. The adsorption rate V and the Freundlich isotherm constant for the different OBCs were fitted first. So we have here the experiment data, kinetic and isotherm data, and the K value and its adsorption rate were fitted first, and using a script written in C# programming language based on the EST equations shown before. So using the fitted OBC and isotherm data for micropollutant, using a second script, the Freundlich constant for the micropollutants were fitted. These two scripts, a mathematical solver was used to minimize the deviation between modeled and measured concentrations. So here we have a screenshot for the model, for the fitting model, and the developed scripts here. This one is for the organic matter, and this one is for the micropollutant. This is the script dialog. The developed script accepts kinetic and isotherm data as input and offers several options for fitting. So I can do the fitting for the adsorption rate V and the Freundlich constant K, or I can do the fitting for KV and the Freundlich exponent. Or I can do it for K, NV, and the non-adsorbable fraction of OBC. However, fitting 4 parameters will result in an overdetermined system, and for simplicity, we advise that the fitting is only done for K and V. So for the fitting of these parameters, algorithms of nonlinear optimization were used. These algorithms were obtained from the open source library NLOpt. And the script offers several solver options, like BobbyQR, Nildamid, and Praxis, and so on. So here you can see the fitting results. If we look here, we have the orange dots represents the laboratory data obtained from isotherm experiments, and here from kinetic experiment. So here we have the fitting of obviously organic matter isotherm data, and here we have the fitting of kinetic data for organic matter. And for here we have also for two micropollutants, benzotriazole and candizartan. You can see that the model meets fits well the data obtained from the laboratory experiments. So in order to validate the model, wastewater treatment plant Mannheim was selected for large-scale comparisons. The Mannheim wastewater treatment plant treats an average of 78,000 cubic meter of wastewater and consists of 4 treatment stages. We have mechanical, biological, PAK adsorption stage, and a filtration plant. And the adsorption stage treats a partial flow of around 300 liters per second and consumes more or less 10 grams per pack of per meter cube. So in order to compare model results with real data obtained from Mannheim wastewater treatment plants, a simulation model for the adsorption stage in the treatment plant was built as shown here. So the PAK adsorption stage consists of a dosing stage. Here we have the effluent concentrations, and here we have the PAK dosing stage, so I can say how much PAK I'm using per meter cube. And we have a contact reactor followed by a sedimentation tank. The volumes and operation scheme were adjusted to resemble the Mannheim treatment plant. A constant PAK dosage of 8 grams per meter cube, contact time of half an hour were set, and the recirculation of PAK was regulated through a PED controller with the total suspended solid concentration of 6,000 grams per meter cube in the sedimentation tank. So looking at model results, they sufficiently meet the 5 days average removal rates obtained from wastewater treatment plant Mannheim. Here, and the blue lines are the model results, and the orange lines or the yellow lines are the clear and the wastewater treatment removal averages for 5 days. Here we can see there is a bit of underestimation for most of the micropollutant, and that can be explained because in the wastewater treatment PAK recirculation was done into biological treatment, and in our model that was not considered. And we expect that when PAK is recirculated, there will be further adsorption or further removal of micropollutants. And model results deviates for candizartan, as you can see here, and sulfamethoxazole quite noticeably. This can be expected because if you look at the figure here, these are the removal rates, the average removal rates for 5 days. And we can see that sulfamethoxazole and candizartan, the removal rates varies largely. So sometimes it's -10 and sometimes it's 50%. So that's why we have quite deviation. So the model was further extended also to include several process control options. So here, as you can see, we have 3 different operation schemes for operation control. We either control the operation with a fixed PAK dose, 10, 12, 8 milligrams per meter cube, or with a preset organic matter removal rate or a preset micropollutant removal rate. What does that mean? That means, for example, I want the 80% removal of micropollutant, and then the model will operate and calculate how much powder activated carbon will be needed in order to reach this removal rate. So this new model has also been integrated into a freely accessible web application, ExpoPlan, for planning sewage treatment plants. It calculates the required volumes of the contact reactor and sedimentation tank, the removal rates for organic substances and organic micropollutants, as well as the amount of powder activated carbon used. It also offers the 3 previously mentioned operation schemes. In a second part, cost calculations are made for construction, mechanical and electrical engineering, maintenance, materials such as PAK and flocculants, energy consumption, and personnel costs. This tool enables the planning of the fourth treatment step using powder activated carbon, as well as process optimization. So here I have the most relevant or the important references that I used. And thank you all for listening.